Hello, my name is Zerar and I'll be explaining you the workflow of the project that me and my team worked on. We worked on it for in our 7th and 8th semester, that is for 1 year, and we displayed it in our college project fair exhibit 2017. We stood second in our computer science department. So the title of the project is Diagnosis of Brain Tumor Using Machine Learning Algorithm. A quick intro about the project. Traditionally, what happens is a person goes for an MRI scan. The MRI report is passed on to the radiologist, and the radiologist has to use his experience and subjective knowledge so as to deduce where the tumor is present and what type of tumor it is. Thus, we wanted to build an intermediate system that takes those MRI scans as input and generates an output that highlights in what portion of brain the tumor is present and of what type. The radiologist would then just have to verify the result and check if the system generated the right result. We obtained our training data from BRATS competition. BRATS basically stands for Brain Tumor Segmentation, and it's an it's a competition held every year that aims at building autonomous system to predict brain tumor. We had 219 patients data, out of which we used 165 for training purposes and the rest 54 for testing purposes. So the MRI scan is nothing but a 3D image of the brain. The 3D image is nothing but a stack of 155 2D images stacked upon one another so as to form the 3D perspective. So this is the data of two patients that I'll be using to run my code. Each of these patients has 5 types of files associated with them. That is 4 type of MRI techniques used, and the last one, that is this one, is the ground truth file that will tell us that where the tumor is exactly present. Since we are using it for the training purpose, we have to know where the tumor is present so that we can train our model. The 4 type of file, that is FLAIR, T1, T1C and T2, these are obtained using different techniques of MRI scans, and each of these technique highlights different portion of brain so as to like find out where the tumor is present easily for the radiologist. So I'll be starting with the explanation of the code. The first and the foremost thing is to normalization on T1 and T1C files because they have a drastic intensity amongst them, so it's important that we normalize them. So what we first do is we grab the path of the data set. The patients variable will have the list of all the patients that we just saw in our HG folder. We had 2 patients data, but the next step is to go inside each of those patients data and to grab the T1 and T1C files. So as we can see in T1S, the T1 and T1C file would be grabbed, and in T1 underscore N4 the normalized files will be grabbed if they are present. If they are not present, then the T1 underscore N4 would be blank. So we'll check first if the normalized file exists or not. If it does exist, then there's no need to run this code and generate those files once again. We can just go on to the next step. But if they're not present, then it's important that we perform the normalization. So for performing normalization, we first grab those T1 and T1C files and we pass it on to N4ITK underscore norm. We'll be applying N4 bias field correction, that is an ANTS interface in NIPYPE. And provide advanced normalization tools to us so that we can simply pass our data whatever we want to normalize and it will give us the normalized output. So we'll pass our T1 and T1C files, the number of dimensions, that is it's a 3D file, so the number of dimensions would be 3, and the number of iterations to perform, that is 20, 20, 10 and 5. So the next step is to pass it on to the N4 bias function. So N4 bias function takes in the input, the dimensions, the number of iterations and the output. We got our output from this variable, that is we'll use the file name of the T1 and we'll just add an underscore n at the end of it and save it in the .mha format. So the rest of the thing is done by the function itself, the N4 bias field correction function. We just have to pass on the output and it would run and generate the normalized file for T1 and T1C. Running this code would be an issue because right now I'm on Windows system and I previously had a Linux system for running these files, but there's some problem with the ANTS interface running on the Windows system, so it throws some kind of error and I won't be able to show it running. So directly going on to the directory, we can see T1 and T1C folders right here, and each of this folder will have a ._n MHA file that is nothing but the normalized file that we just created from that code. So the next step is to convert those 3D images, that is the 3D files, into 2D ones. As we can see right now, all the folders are empty, that is info folder and label folder, and we'll be running our code and extracting the 2D images from those stack of 3D images. So first we'll be extracting the 2D images of the info folder. We can see that patient zero's data is right now being processed and extracted, and patients one data, since we have two patients data in our data set right now. So we have successfully converted our 3D images into 2D images, as you can see in this folder. We can see that each of those flat T1, T1C and T2 images are being extracted and then combined in one PNG. So what we did right now was we had the original images in this format, and as you can see the intensities are quite off and we have to normalize it. So this is how a mathematically normalized slices looks like, and what we applied was n for bias corrected slices. So as we can see the intensities of this are quite average. So this is the code for generating that is extracting the images from the MHA files and storing it into the PNG format. First we'll grab the patient's data from the dataset, then we'll pass that data to the init patients function. We'll create an object of a class called brain, and we'll be assigning it and pushing it onto the patients list. So the next step is to run this patients list one by one and to create the PNGs for each of the file and then stack it on one another. So as we can see here, we have 5 kinds of mode, that is flat, T1, T1C, T2, and GT stands for ground truth, that is the file that tells us where the tumor is exactly present. As we saw right now, we had 240 cross 240 image and 5 kinds of image stacked on one another, and we had 155 such slices. So each of these variable reads the different kinds of files, and then we simply perform the extraction process, and then we stick it on one another so as to create that array of 5 images on one another. Then we simply use the path and then store it in the .png format, as we can see right here. So basically what this file does is it reads the MHA file of each type, that is flat, T1, T1C and T2, and then extracts the 2D images from it and stack it on one another. So the next step is to generate a sequence of labels. That is, each of the label file will have a pixel value associated with them: 0, 1, 2, 3 and 4. That is, 0 means nothing, 1 means it's a edema, 2 means it's a necrosis, 3 means it's a advancing tumor, and 4 means it's a non-advancing tumor. So I'll be running the code right now. We saw earlier that the label folder was empty, but now it has been filled up with the patient's data. We can see the 0 right here is the 0 number patient's data, and 1 would be the first number patient's data. And the image looks blank because it's nothing but a collection of pixels with the value 0, 1, 2, 3 or 4, and we can't see it with naked eyes, but the pixel has some values in it. So we extracted the label part from the ground truth file, that is from here. This is nothing but this will tell us where the tumor is present. This is used for training purposes. So the next step is to extract patches and then save patches for training the classifier. So how do we extract patches is So we read the training data from our info folder, that is the stack of 155 images of 5 types, and then we pass it on to our patch library where we generated 33 cross 33 patches from the training data, and we provide number of samples, that is how many type of samples we want for each of those class labels. We saw earlier that we had 5 class labels from 0 to 4 that each represents a different kind of tumor. So we pass it on to the patch library, and what patch library file does is basically it patches the 240 cross 240 image by 1616, and then the value of the centermost pixel is picked up and then checked that in the surrounding area, are there at least 10 instances of that pixel that was in the middle. If there is, then that middle pixel becomes our class label, stored as a class label. So we first randomly picks up a file, and then we randomly picks up a pixel and checks if the surrounding have the at least 10 instances of those pixels. So this is how we generate our patches, and then we save those patches. That would then be used in our classifier. We'll pass the patches to our classifier and then train it, and then we can use our prediction algorithm to predict from based on those patches that a tumor is present or not. This is a helper class that we created for using different kind of functions that we needed: the overlay segmented image on one another, pat predicted image, and etc. We had this function for generating how much accurate our result was. So the next and the final step was to save the classifiers. As we can see, we use different kind of classifiers, that is different models: k nearest neighbor, random forest, SGD, SVC, and linear SVC. Each of these different models gave us a different accuracy, and so we can see we used different models, that is k-nearest, support vector machine, random forest, and stochastic gradient descent. So this is how accurate our result was using the KNN, that is 88.62%. SVC gave us a 91.05% accuracy. This is the ground truth file that we already have, and this is what our model predicted. And as we can see, there are quite some noises and a wrong prediction right here. Next is linear SVC, and it generated a very noisy output. Next was RFC, and as we can see, RFC generated quite accurate output on the type of tumor present. The location was a bit off, but the type of tumor was pretty accurate. And SGD on the other hand had the most promising result for the location. So what we did was we combined SGD and RFC, that is we used the location produced by SGD and the type of tumor produced by RFC, and then we overlaid them on one another so as to get an accuracy of as good as 97%. You can see this is the original tumor present, this is what SGD predicted, this is what RFC predicted, and by overlaying SGD on RFC we got something like this, which was pretty accurate than the other models that we used. So this is our final classifier that we used, that is the combination of SGD and RFC. So we have to provide 5 types of arguments with it, that is the patient's MHA folder, the path to the SGD prediction, path to RFC prediction, the output directory, and the patient's identifier. So we call upon the predict patient function. Here it is. So what it does is we first take the patient's data that we want to predict, and then we do all those things that we did earlier, that is we convert it into a 2D images, we normalize it, then we extract patches from it. So as we can see that after generating the PNGs of the patient's data, we pass it on to the SGD path and the RFC path, that is these are the classifiers that we use, and then it gives us the SGD and the RFC output. So the next step what we did was we used the SGD's location and we overlaid it with the RFC's type of tumor data, and we then saved it as the prediction NPY. Then we had to calculate the accuracy, that how accurate our result is. So we calculate the accuracy by mapping how much of the predicted data matches with the original data divided by the total number of pixels present. So this was our project, and as we can see, we had achieved at least 97% of accuracy in it. But this was all circumstantial because we used 1 lakh patches to train our model, and for different kind of data we got different kind of accuracy. So the overall accuracy of the project was never found because we didn't have enough computational power to calculate it or to train it on more patches. We tried using 50,000 patches, that is 10,000 for each of the classes, and we tried predicting it using it 10, but it didn't show promising results. So we increased our patches to 1 lakh patches, and then we tried doing the same, and we got this much accuracy. We were hoping to increase our number of patches, but we didn't had enough computational power.